So, today in this lecture we shall proceed how to account for solar tank losses in the solar energy system, which is being calculated by the Fibonacci chart method as well as the finite heat exchanger. So, we shall just recall the correlation f in the Fibonacci chart method is given by phi bar max y minus 0.015 exponential 3.85 f minus 1 times 1 minus exponential minus 0.15 x dashed times standard storage to actual storage ratio raised to the power 0.76. So, this takes into account the non-standard storage. So, now how do we include the tank losses? If the tank is at a average temperature of T t, it will be losing heat at a particular rate depending upon the overall loss coefficient of the tank multiplied by the surface area of the tank times the temperature difference of the T tank minus the surrounding T a dashed. Initially, we do not know what is the tank temperature. So, but let us say q dot tank is the rate at which energy is lost from the tank. Since I do not know the tank temperature, I will guess a tank temperature which may require iteration. So, this I will call it guess 1 and let this be T T 1 and the surrounding temperature may be T a dashed. Please note that this may be different from the ambient temperature, since many times the storage tank can be in the basement and the basement temperature, if it is heated, could be quite different from the ambient temperature. So, we will call it, to keep it general, T a dashed. So, q dot tank is U a of the tank times T T 1 minus T a dashed. So, this U a tank is the overall loss coefficient watts per meter square degree C multiplied by the surface area of the tank. So, will be in watts per degree C, just like which we have introduced in calculating the space heating, the building heat loss coefficient U a h. If I integrate this q dot tank rate over the month and assume this T t dash and T a dash remain constant or some average value, I will get U a tank. It should not differ so much with the temperature. T t 1 minus T a dashed times delta T, where delta T is the number of seconds in the month. This makes it joules. If U is in watts per meter square degree C, this will be so many joules, number of seconds in the month. Okay. So, what I shall do is assume load now will be equal to let me say L 1 L plus Q tank. The effect of the tank loss as far as the solar energy system is concerned, it looks like a additional load. So, if I calculate my y and x dashed with L plus Q tank, I do not want to complicate it unnecessarily calling L 1, L 2, L 3 etcetera. So, it is the actual load on the system plus the loss from the tank. I will get the solar load fraction, but I shall qualify it as FTL, that is inclusive of the tank losses. So, what I will get this number is Q system by Q tank by L plus Q tank. We have not deviated from our original definition, except we realize that Q tank has been fully met and has to be fully met, and the load on the system is L, and Q s is the amount of energy that is going to meet the load on the system L. So, consequently, the load fraction that I obtain will be Q s plus Q tank by the total load now being L plus Q tank. But actually my F solar is Q s by L. So, from this I can find out F is equal to Q s by L, just divide throughout with L, that I will get as F T L times 1 plus Q tank by L minus Q tank by L, right. Q s by L will be F, then Q tank by L will be there, which is over here, and L by L is 1 plus Q tank by L. So, that goes on to F T L minus Q tank by L. So, this is nothing but you respect the tank losses, you fully meet that, then the remaining amount of energy goes to meet the load. Now, there are two limiting cases, because I must have a way of correcting the T T 1. Limiting cases to estimate tank losses. One, a low estimate assume that the tank is at T minimum, because the system is supposed to deliver energy at or above a temperature of T minimum, the tank temperature cannot be lower than T minimum. And an upper limit is the assume that the tank is at the average collector inlet temperature. This is essentially equal to the outlet temperature, because when once it stops increasing, the pump is cut off. So, this I will call it T I bar. Now, so that this T minimum is no problem, this is known, is specified. This T I bar I will estimate from phi bar relation. Since this is corresponding to a inlet temperature of the collector, based upon this inlet temperature there is a certain utilizability phi bar, and if there is a certain utilizability, what is the T I bar temperature. Now, this is where this phi bar, I am deliberately not writing phi bar max, just phi bar. It is essentially F T L upon phi. In other words, if Y is the non-dimensional absorbed energy and F T L is the load fraction that includes of the tank losses, then that corresponds to some sort of a phi bar Y equal to F T L. As I was telling, phi bar max into Y is the maximum solar load fraction. So, some average utilizability multiplied by Y should be my solar load fraction with the tank losses. So, now the new tank temperature, or at least I have got a basis, should be somewhere in between these two numbers. T tank 2 I will call it, T I bar plus T minimum by 2. Now, this T tank 2 may not be equal to, first guess, T tank 1. So, repeat the process. If T tank 1 minus T tank 2 to be make sure modulus is, let us say, greater than 0.1 degree C, or stop if T tank 1 minus T tank 2 mod is less than 0.1. In general, if we continue to iterate, I can write it as modulus of T tank n minus T tank n plus 1 mod is less than 0.1 degree C. So, you continue to this calculation n number of times until the difference in that estimated T I bar and T minimum by 2 is pretty close to the previous value you guessed as the tank temperature. So, let me quickly go through this again. So, that step by step, 1 guess T T, 2 calculate Q tank, 3 treat Q tank as an additional load, 4 obtain F T L inclusive of the tank losses, from which you can calculate F solar in meeting the load on the system, and 5 new tank temperature is T I bar plus T minimum by 2, which may be your T T 2. T I bar is calculated from phi bar equal to F T L by Y. Because this is a function of exponential a plus b times x c bar plus c x c bar square, I will find out an x c bar. From that x c bar, I will find out T I bar. Okay. F T L by Y, I am sorry. So, this process is continued iterating n number of times until the temperature difference that you have assumed to be the tank temperature and this final average tank temperature, which is an average between upper estimate and lower estimate of the losses, is pretty close to each other. So, now the procedure is clear, which shall become even more clear when we solve one example after some time, little time later. Now, finite heat exchanger. If you want to briefly say how the tank losses are accounted for, but for the iterative process and guessing, we might say that the effect of the tank loss is to enhance the load on the system by the amount that the energy is lost from the tank. Now, if you have a heat exchanger, from the tank it goes to the heat exchanger to meet the load. So, if you think about in the backflow, the T minimum, the temperature at which the energy is to be delivered by the collector, shall become higher if H x is heat exchanger is present, right. That will be some delta T is required, that delta T reflects in the tank temperature, that tank temperature reflects in the T minimum or the outlet temperature from the collector, which needs to be delivered in order that it finally supplies energy at the originally desired T minimum. So, once again I will assume that T min guessed 1 equal to T min plus some delta T 1, which may be 4 degrees, 3 degrees, like that. So, delta T 1 is the first guess. So, we follow a phi bar F chart procedure. What do we mean by this? T min 1 correspond to some phi bar max, okay, or in between if you want T min 1 corresponds to x c bar min 1 corresponds to phi bar max. Then I will get my solar load fraction. Y and x are straightforward to calculate, because they do not depend upon a T minimum. When once if you want you can now x c bar minimum rewritten will be I c minimum by I t noon equal to, everything is the same, F r u l, write T min guessed minus T a bar by F r tau alpha bar over R T n R n K T bar H z bar bar. This is nothing but the same previous definition, except I am replacing the minimum temperature at which energy delivery is desired by T minimum plus some delta T, because of the presence of the heat exchanger. Now, if F is the solar load fraction, that means phi bar I have already calculated, x c corresponding phi bar max, x c bar minimum, and we know y and x dashed, and we know F. So, if F is the solar load fraction, that multiplied by y is the useful energy that is being sent. So, that will be equal to q s by, I will explain again, delta tau L by epsilon L C minimum. The energy that is going to meet the load on the system is F nothing but L product by delta tau L will make, this is number of seconds that the load operates, that the load exists. it may not be 24 hours, it may be, let us say, 12 kilowatts for 12 hours a day by epsilon L C minimum. So, this is a rate at which the energy delivery is made upon epsilon L C minimum, and you will be very comfortable if you look at the equation as epsilon L C minimum delta T 2 is nothing but the energy transferred by the heat exchanger, right, because this is the minimum of the heat capacitance rates of the heat exchange fluids on the two sides of the heat exchanger multiplied by the effectiveness of the heat exchanger multiplied by the delta T available across the heat exchanger. Okay. This is nothing but F L upon delta tau L. So, F L is the total amount of energy supplied over a period of delta tau L. So, this is the rate at which the energy is supplied, and that should be matched by the heat exchanger of effectiveness epsilon L and the minimum capacitance of C minimum with a temperature difference of delta T 2. So, why I am emphasizing is delta tau L may differ from number of seconds in the month, right. Now, you might ask me the question, why did you not do this for Q tank estimate? The loss from the tank always takes place, whereas, if there is no load, heat exchanger does not operate. That is the reason by energy, this is a rate epsilon L C minimum is a rate at which the heat exchanger is going to supply the energy. This is the rate at which the load is on the system. So, again we will set up the same condition. First guess, the difference between these two should be, let us say, 0.1 degree C, or else repeat if is greater than 0.1 degree C. So, you always come out with delta T 2 and then go and re-estimate your x c bar minimum and then the solar load fraction. Okay. So, in a nutshell, that once again the heat exchanger effectively increases T minimum. So, the procedure is T min equal to T min plus delta T, which may change it to x c minimum, from where you calculate phi bar, from where a nu f. So, from this epsilon L C minimum times delta T 2 should be equal to f into L by delta tau L. So, this is the governing equation. How please do not follow in the context, these are not delta T squares, delta T 2, but I suppose those of you who have heard my repeatedly saying this, you will not make that mistake. Okay. So, this is what I have again summarized: treat tank loss as the additional load of the system, treat the effect of heat exchanger is to enhance the minimum temperature above which energy delivery is desired. So, if you remember these two things in physical terms, it is more easy to automatically follows the procedure. Only in the case of tank temperature, a new estimate of the tank temperature is T I bar plus T minimum by 2. So, the T I bar being coming from the average utilizability concept. Now, we shall to consolidate these ideas, we shall take up a example and we shall see how much we can do. And I am deliberately giving many relations which we have gone through earlier. In fact, if you solve this problem, more or less almost all the methods that we have covered would be covered. So, the location is at a latitude of 40 degrees N. In fact, this example is from the textbook by Duffy and Beckman, except few things I have changed here and there, and this is for a process heating system. This is to bring out certain details, and flat plate collectors facing south, and the slope beta is equal to 40 degrees, area AC equal to 50 meter square, and the collector parameters are FRUL is 2.63 watts per meter square degree centigrade, and FR tau alpha normal. In fact, these values we have used in other publications also. This is sub T minimum is 60 degrees C of 12 kilowatts for 12 hours a day. Okay. Now, for our calculations, you may assume ground reflectance to be 0.2. So, the characteristics you should note is, of course, the location, slope, flat plate collector, the collector parameters, and then the minimum temperature and the total load. And of course, this is the area that we have provided. What is the solar load fraction that comes out, which may not know? We do not know a priori. The idea is to calculate it. And if you plot the annual solar load fraction, it may be something like this. And if you have this is 50 meter square, this may be 0.52. Whereas, if you make any one monthly calculation, so for January it may be less, for June it may be more, because the solar radiation is more and the load on the system is constant, it is 12 kilowatts for 12 hours a day. So, I will take the data of January, which you can calculate from the TM/2 also. H bar is 8.6 megajoules per meter square day. In order that there is no ambiguity, the monthly average daily radiation on a horizontal surface is 8.6 megajoules per meter square day, and the ambient temperature is T A bar is equal to -5 degrees C. Now, only a difference is, if you take a location from India, typically T A bar may be 10, 15, 20, whatever, even in the month of January. So, first, since we know we are going to use phi bar F chat method, my first question will be, what is the critical radiation level? So that I try to put it in the form that you proceed, so that the methodology is remembered. What is the non-dimensional critical radiation level? And then you have C monthly average reutilizability, and what is the solar load fraction met by the system. Have I forgotten anything? Yeah, I think let us assume standard storage. Okay. It is 350 kilojoules degree C. These are one by one we try to calculate. Also, first part negligible tank losses, and infinitely large. I suppose those of you who are familiar with heat transfer, you would not find it surprising when I say infinitely large heat exchanger. It is nothing but saying that delta T is 0 across the heat exchanger. Okay. So, first we need the mean declination. You can see this is almost one of the very first relations we have written, 23.45. The whole idea of 284 plus n by 365 into 360, that will be equal to 23.45 times sine 284 plus 17 by 365 into 360. Of course, n is equal to 17 from the table, or you can use n is equal to 15 for January 15 without much, it does not make a second decimal. That should be minus 20.9 degrees. It may be 0.88 or 0.92, I do not know the nonlinearity. So, this is the mean declination from which we calculate the sunset hour angle omega s, which is once again cos inverse minus tan phi tan delta, which is, do not worry about this delta and delta m, we are making only mean day calculation. So, even if you forget the subscript, it means it is a single number in this problem. Okay. This comes out to be 71.3 degrees. So, this is lower than 90 as can be expected at fairly high latitude, and in January it will be less than pi by 2, lower value. And omega s dashed for this south facing surface, we know trigonometry, obviously this will be lower than that cos inverse. However, you can calculate by minimum of 71.3 and cos inverse minus tan phi minus beta tan delta, which is 71.3 degrees. What next? Because all my correlations will be in terms of the clearness index, I need H 0 bar, which will be 24 into 3600 times GSC, the solar constant, by pi times 1 plus 0.033 cos 360 n by 365 times cos phi cos delta sin omega s plus 2 pi omega s by 360 times sin phi sin delta. Please see this factor 2 pi by 360 same as pi by 180, because omega s I am going to put in degrees. That is once again 24 times 3600 times 1357 or 63 as the case may be by pi times 1 plus 0.033 cos 360 into 17 by 365 times cos 40 cos minus 20.9 sin 71.3 okay, fine, it's all right, not necessary, plus 2 pi into 71.3 by 360 sin 40 sin minus 20.9. You can check up with your relation which we have given n number of times, that comes to 14.4 megajoules per meter square day. So, the monthly average clearness index is h bar by h 0 bar, which is 8.6 by 14.4 equal to 0.6. Okay. So, from this we can calculate again monthly average daily diffuse fraction. This is Collatz-Pereira-Raval's correlation again. Which is 0.775 plus 0.006553 times omega s minus 90 minus 0.505 plus 0.00455 times omega s minus 90 times cos 115 80 bar minus 103. Please check these equations and the brackets. I think I am copying all right, but sometimes there may be mix up. 0.3 is reasonably expected in the ballpark value. So, R bar will be h t bar by h bar, which can be written as 1 minus h t bar by h bar. Now, you understand why we calculated this, times R b bar plus h t bar by h bar times 1 plus cos beta by 2 plus rho, which is 0.2, minus cos beta by 2. This is the tilt factor for the entire radiation. This is the beam component, direct component, this is the diffuse, this is the ground reflected. And you have your R b bar cos phi minus beta cos delta sin omega s dashed plus sin phi minus beta sin delta omega s dashed into pi by 180 by cos phi cos delta sin omega s plus sin phi sin delta omega s into pi by 180. Oh, please note that the numerator is with the apparent sunrise sunset hour angle. So, I am deliberately writing omega s dashed and omega s dashed, and the denominator is with respect to the actual sunrise or sunset hour angle omega s. So, simply because these are numerically equal, do not interchange, that will become a bad habit. So, this R b bar, if you calculate it, it is 2.32 and R bar will be 1 minus 0.3, that is h d bar by h bar into R b bar 2.32 plus 0.3 times 1 plus cos beta by 2 plus 0.2 into 1 minus cos beta by 2, which is 40, and this comes out to be 1.91. Let us just halt for a while. So, in the course of this problem so far, we used the how to calculate the declination, how to calculate H 0 bar and the clearness index, and then the diffuse fraction and the parameter R bar. So, tilted radiation, diffuse fraction, extraterrestrial radiation and declination, these relations have come so far. Now, we will go for estimating R t at noon time, because what was the first question? The first question was, what is the critical radiation level? If I want, I can calculate f r u l into T I minus T A by something, from which we have to calculate the non-dimensional critical level. If I want to calculate the non-dimensional critical level, we need the noontime radiation on the average day. R T n is pi by 24 a plus b cos omega. Again, Collares, Pereira and Ravel, these relations which we have written earlier, cos omega minus cos omega s by sin omega s minus 2 pi omega s by 360 cos omega s. This is to be calculated noon, means omega is equal to 0. Typically, it may not be at times. So, however, we will do it at omega is equal to 0. Assume solar time is the same as the local time, that is one part, and there are certain instances where omega may not be equal to 0. A 0.409 plus 0.5016 sin omega s minus 60, and a B is 0.6609 minus 0.4769 times sin omega s minus 60. So, if you calculate, R T n will be 0.178. Okay. Now, you start developing a feel for the numbers. Your R factor, R b factor is higher, R factor will be less, because that will be multiplied by 1 minus h d by h. So, this is 1.91 R bar, and R b bar is 2.32. Later on, when we make a calculation similarly for summer, then my R b bar and R bar factors will be smaller than what you have got for the winter months. So, R T n is 0.178, this is about the noon time, that means 11:30 to 12:30, and that is almost 0.178, means 20% of the total radiation. It can be expected, though it is only 1 hour, and the total hours are less than about 11 hours. Okay, 90 hours corresponds to 6 10 hours, 10 and a half hours. So, 20% can be expected in one single hour, because it is around the noon time. So, this is one way you can check whether the numbers that you get are reasonable or not. For example, RTN should be higher than the proportionate amount around the noon time, and it will be lower than, that means if there are 10 hours, or each one will be 0.1, but around noon time it is almost 0.2. Okay. And RDN is simpler, that A plus B cos omega also is not there. Cos omega minus cos omega s by sin omega s minus 2 pi omega s by 360 cos omega s. This is .164. Let me repeat, 0.164. Now, you might wonder, the diffuse radiation RDN, the fraction, also is 0.164, pretty close to 0.178, but you should remember this is 20% of the diffuse radiation, whereas this is about 20% of the global or the total radiation. Okay. So, these numbers look similar, order of magnitude, they do not differ much, because one is normalized with respect to the global radiation and the other is normalized with respect to the diffuse radiation. So, I am just trying so that you can develop a sense of feel for the numbers that you will get. It can't be 10 to the power 6 and 10 to the power minus 3 or so. Now, we were emphasizing for some reason or the other R factor at the noon time in calculating the non-dimensional critical level. I need H d by H, right, at clearness index daily is numerically equal to average clearness index. Okay. So, whereas when we calculated R bar and R b bar, we used H d bar by H bar, whereas when we are going to calculate R n, I will use H d by H. Again the Kollaros-Pereira-Raoults correlation, but the individual daily diffuse fraction correlation. There may be different theories or the explanations for this. One simplest could be this may be working better as a correlation. The other reason could be, since the critical level is going to be found out on the noon time equal to this solar radiation on the mean day, no matter what it is, mean day is a single day. So, we shall use the single day's diffuse fraction. In other words, for equating it, it will be the individual diffuse fraction that matters. Incidentally, k T bar is a number, that is all. See, this bar I should not have drawn it, plus 14.648 k T to the power 4. So, if you calculate, this is 0.41. So, at the given numerical value, at least in this range, it looks like the daily diffuse fraction is higher than the monthly average diffuse fraction. That is some time back also I have explained, H d bar by H bar is not summation of H d by H divided by n, but it is summation of H d by summation of H. R b at the noon time cos phi minus beta cos delta cos omega plus sin phi minus beta sin delta by cos phi cos delta cos omega plus sin phi sin delta. So, R B noon will be 1.97. So, R n, as I have explained, 0.164 by 178, that is R d by R t into the diffuse fraction 0.41 times 1.97, that is R b noon, plus again R d by R t times the diffuse fraction 41 times 1 plus cos beta, which is 40 by 2, plus the ground reflectance 0.2 into 1 minus cos beta by 2. This comes to be 1.59. So, R bar upon R n equal to 1.91 by 1.59 equal to 1.20, right. So, this is one parameter I need in calculating phi bar, in addition to is a function of course, that A, B, C, and then R n by R bar or R bar by R n, does not matter, and X c bar. So, this we have obtained. This can be calculated straightforward from the clearness indices. Now, the critical radiation. I see FRUL to T min minus T A times time is important, that is what I was telling. You have to put that factor by 0.72 into 0.94. This now you will have in 909,308 joules per meter squared in that hour. That will be 0.909 megajoules per meter squared hour. Okay. So, this is necessary, otherwise you will get a very small number. It should be watts per meter square, but then I had to adjust the other thing also accordingly. So, non-dimensional critical level will be X c bar will be I c by I t noon time, that is equal to, now we got 0.909, which is R t n into R n into H bar. This is H bar, R n and R t n. So, this will be 0.909 by 0.178 into 1.59 into 8.6. This is in megajoules, this is also in megajoules. So, I had no problem, 0.37. So, we calculated up to the non-dimensional critical level, then we will go to the calculation of the utilizability and the solar load fraction met. Okay, now, I think many of the relations which we have developed or studied empirically or analytically, they are already under use. So, if you solve one problem on phi bar F chart, almost all the relations you will recall. Okay. We shall continue next time. Thank you.
Bye.